Alright, describe the figures that make up each composite figure. The curve is a semicircle. Alright, part A, let's look at here. We see a rectangle with a semicircle. So it's a rectangle next to a semicircle. Part B, we have a square, you can tell because all four sides are the same, with a circle cut out of it. So this composite figure is just this yellow part. It's a square with a circle cut out of it. Here we have a parallelogram with a triangle next to it, a right triangle specifically. And that's the answer for question 1. Question 2, describe how you would determine the area of each composite figure in question 1. Well, here I would find the area of the rectangle, which would be the base times the height. Here then I would find the area of the semicircle. Well, full circle would be, the area of that would be pi r squared. And so I'd have to find the radius, and then I'd do pi r squared, but then I would divide by 2, because this is only a half of a circle, so it's only going to be half that area. And then I would add them together, whatever the area of the rectangle was, plus the area of the semicircle. Here I would first find the area of the square by doing base times height, or side squared, because both of them are the same. And then I would find the area of the circle. First I'd have to find the radius of the circle, and I would do pi r squared. And then I would subtract the area that I got of the circle from the original area of the square. Right? So it's this full square minus the area of the circle, because it's cut out. Here I would take the area of the parallelogram, which will just be the base times the height. If it doesn't give me the height, then I'll have to find out what angle this is, and I can use SOHCAHTOA. If it gives me this side length, I could use SOHCAHTOA to find this height here. Right? So if I know this side length and I know this angle, I could say the sine of this angle is equal to this height divided by this side, opposite over hypotenuse of this little triangle. And then I could solve for this. Once I know this height, I can say that the base times the height is the area of this parallelogram, just like a rectangle. And then I would do the same thing for the triangle, but this would be the base times the height divided by 2. Right? If it were a rectangle, it would be base times height, but since it's a triangle, it's half of that. Then I would take the area of the parallelogram and I would add it to the area of the triangle. Alright, sketch the figures that make up each composite figure. Include measurements in your sketches. All curves are circles or semicircles. Alright, there are several ways of doing each one of these. For example, here we have a trapezoid down here. You could also call it a rectangle with a little triangle here and a little triangle here. So there are different ways of seeing things, but I'm just going to go with it. Alright, so we're going to start off and call this a rectangle. So draw a little sketch of that rectangle. And that is 40 by 30. Plus, there is a trapezoid here. Boom, 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 boom. The bottom is 25. The top is 40. And the height is, let's see, 60 minus 30, so 30. Alright, for question 4a, we just have to determine the area of each composite figure, so determine the area of this. Well, looks like the area of the rectangle is base times height, 40 times 30, and that is 1200. And the area of the trapezoid is the average of the smaller base times the height and the larger base times the height. So the average of 40 and 25 is, let's see, 32.5. So the area of this one is 32.5 times 30. That's 975. 1200 plus 975 is 2175. Notice I didn't use any units in my calculations, but I will definitely use the proper units in my therefore statement, and my drawings I should always use the correct units as well. Alright, part B, we have a triangle and a rectangle. So here's my sketch. these measurements were given. This 4.1 is obvious because the total height here is 7.6, but 3.5 of it is this area, so the rest is 4.1. All right, let's find the area. Area of a triangle, base times height divided by 2. Area of a rectangle, base times height. Total area is these two added together. So area of the triangle, we get 15.225. Area of the rectangle, we get 35.67. Add them up, you get 50.895. That was easy. All right, part C. We just have a big circle and a small circle. Big circle minus the small area of the big circle minus area of the small circle will give us the total area of that ring. Part D, we have a rectangle, but we have to subtract a semicircle. And so the area of the rectangle minus the area of the semicircle will give us the total area. Now there is a bit of a trick here. Here you see 3 feet, whereas here you see 15 inches. So feet and inches aren't really jiving. This guy's in inches as well, so we're going to put it all in inches. There are 12 inches in a foot. So 3 feet, that's the bigger one. We are going to multiply by 12 to see how many inches, so 36 inches. All right, so the area of this rectangle is actually 36 times 15 if you're doing it in inches squared, which we will. This semicircle is going to be pi r squared divided by 2, so pi times 7.5 inches times 7.5 inches, and divide that by 2 because it's only a half a circle, not a full circle. All right, as we can see, the area of the rectangle is 540, the area of the semicircle is about 88.4. And so the total area is about 540 minus 88.4, which is 451.6. Again, to make life easier on yourself, always write the units, so inches squared, in the actual answer. And if you have a drawing, you might as well throw it in there. But it's really not worth throwing it in your equations. Well, here, I mean, it is kind of in an equation, but that's just converting between feet and inches, so you obviously need the feet and inches in there. But generally speaking, when we're doing calculations, we don't really need to make it more confusing with all of the units. I notice I did not say 451.6 squared. This number is not being squared. This is the total number of little squares that are 1 inch by 1 inch that could fit inside this area right here. Okay, so it's saying that inches squared is the measurement, like the unit of measurement. So it's saying little tiny 1 by 1 inches. There are 451.6 that fit inside here if you cut them properly. All right, number 5. 2 students are calculating the area of this figure right here. Tasman's method. This is a rectangle with a trapezoid on top. I will add the area of the rectangle to the area of the trapezoid. Jeffrey's method. This is a rectangle with a triangle removed from the corner. I will subtract the area of the triangle from the area of the rectangle. So who's correct? Let's justify our answers. Include a diagram in our explanation. All right, let's start with Tasman's. This is a rectangle. Yeah, I see the rectangle right here. With a trapezoid on top. Yep, this is a trapezoid on top. Trapezoid means that it has 2 sides that are parallel and 2 sides that are not necessarily parallel. Okay, so just a reminder, trapezoids people have a hard time with. If we were to find the area of the trapezoid, the way I like to see it as I take the smaller side between the 2 parallel sides, and I pretend that that's the real side. That's a rectangle. That will be too small because we're missing this little triangle part. Then I think about taking the big side, which is the bottom side, times the height, take the area of that rectangle, and that's too large because it's this much. This triangle's not supposed to be in it. But the actual area is the average of those 2 rectangles, of this yellow rectangle and of this bigger green rectangle. Okay, so the actual area is halfway in between that. So the area will be, let's see, you get that smaller base plus the larger base, which is the bottom base. And you take the average of those 2 by adding them up, divide by 2, and then you take that and multiply by the height. Okay, I just thought I'd give you a little extra tidbit. That's how some people sometimes have trouble solving the area of trapezoids. Anyway, yep, Tasman looks like she's doing well. Good job, Tasman. Jeffrey's method. Jeffrey says that we have a rectangle. He looks at this as a full rectangle, which is true, with a triangle cut out. So he's going to do the area of the rectangle minus the area of that triangle. Yeah, that'll work as well. So it looks like they are both correct. Include diagrams in my answer. So I'll just write all that out. I've already explained it, and we're done. All right, 6A. This is a circle, well, semicircle, sorry, with another semicircle cut out of it. The area of each circle is pi r squared, so each semicircle is pi r squared divided by 2. So plug that into a calculator. The top one gives you 25.1 approximately. All right, the bottom one gives you about 6.3, and if you do a simple subtraction, you get the total area is approximately 18.8, and that is in feet squared, so therefore the area of the shape is approximately 18.8 feet squared. Alright, let's go to part B. Part B looks like it is a rectangle with a triangle attached. We do have to worry a little bit about a conversion here, because right here we have 3 feet, and these are in inches. So we do have to convert from feet to inches, but we know that we can just multiply by 12. So instead of writing 3 feet, we can write 36 inches. We've already gone through that on a previous problem, which is really nice of them, because now this rectangle we know is 15 times 20, the area, and this triangle, they actually gave us the perpendicular height, right? Because if this whole thing is 36 inches, then 36 minus 15, this height must be 21 inches, and we don't have to use sine, cos, or tan to calculate it. Right, so the area of this triangle is simply 20 inches times 21 inches divided by 2. Alright, so the rectangle, 20 times 15, that's 300. For the triangle, 20 times 21 divided by 2, 210, and the total, 510, and that is in inches squared. And I always like to remind my students that just means that if we had a bunch of squares that are 1 inch by 1 inch, that means 510 of them would fit into this if we cut them all up to fit this shape perfectly. Exactly 510 would fit inside there. I like to mention that because as we move on to volume, then we're going to be talking about cubes, and you're going to see inches cubed. And when you see inches cubed, you have to know that we're just saying we're measuring using these cubes. Right? How many cubes can you fit in? Right now we're just measuring using these squares because it's a flat surface, so you need a flat square to see how many of them you can fit onto your shape. Right? If it were just inches, well then we would just be measuring straight up a distance across. Right? We're not putting a whole bunch of squares on a straight line, because squares don't fit on a straight line. It's too thin. Right? So when you're measuring in squares, you're measuring the area. It's like there's enough room to put squares inside it. Alright, part C, we have ourselves a rectangle here attached to 2 triangles on the top and on the bottom, and a semicircle. There's nothing cut out, so we just have to add up the area of the rectangle, the 2 triangles, and the semicircle. This is 18 all the way up and down. Now it doesn't tell me what this little area is, so I'm actually going to use a trick. I'm going to take this triangle, and I'm going to put it next to this triangle and make it one big triangle. That way we do know the base and we know the height. Right, since we know the base of the diameter of this circle is 10 centimeters, so that's from here to here, then we know this plus this together is the rest, so 8 more centimeters. Alright, so using that trick now, we can say that this triangle is actually these 2 little triangles together. We're going to find the area of that. That'll take care of both of these. Then we'll take care of the area of the rectangle and the semicircle, and we'll have our total area. Right, so the area of the rectangle, let's start with that actually. Area of the rectangle is 12 times 10, that's 120. The area of this triangle is base times height divided by 2, so 8 times 6, or 8 times 12 divided by 2, which is 48. And the area of this semicircle is, remember, don't use 10 because that's the diameter. We want to use 5, the radius. So pi times 5 squared divided by 2. That's about 39.3. Add them all up, you get about 207.3. That is, they're all in centimeters, which is lucky, so that's in centimeters squared. Remember, it's a flat surface, so the only way to measure it is with little squares, so centimeters squared. All right, we'll move on to question number 7. A grocery store display is built using cans of juice stacked in layers. The display has 10 layers. The top 3 layers and an overhead view of each of these layers are shown. Describe the pattern in the number of cans in each layer. What shape is each layer of the display? How many cans are in the 10th layer? Each can has a diameter of 12.5 centimeters. Determine the amount of floor space needed for the display. What assumption are you making? All right, A, describe the pattern of the numbers of cans in each layer. Well, the first layer has 1, the top layer. The next one has 4. The next one has 9. So it looks like it's 1, and then you're going to have 2 rows of 2, and then 3 rows of 3. So it looks like we're going to have 4 rows of 4 in the 4th, 5 rows of 5 in the 5th. All right, so basically the number of cans, well, this is going to be 3 times 3. 2 times 2, 1 times 1, so we're going to have 4 times 4, 5 times 5, 6 times 6. So it's just whatever layer you're on, it's that number times itself. So that's right. The number of cans in each layer is just equal to that layer, like the number of that layer squared. All right, B, what shape is each layer of the display? Some people might say the shape is a square because they're kind of made to look like a square. I would say it's, I don't know, a composite shape of several circles. How many cans, this is for part C, how many cans are in the 10th layer? Well, I mean, that's answered with our part A, right? Each layer is just the number, whatever the layer is, squared. So I guess there'd be 100 cans in the 10th layer, right? 10 squared equals 100. Right, part D, we'll do it up here. Each can has a diameter of 12.5 centimeters. Determine the amount of floor space needed for the display. What assumption are you making? So you can look at it a few different ways. The circles are touching each other, but there's space in between all the circles still. But that floor space isn't really going to be usable. If it's like the floor space between the cans isn't going to be usable. I suppose you can use the floor space in this little area if you want, but I would say probably you're going to draw a square around this and say, look, we're going to need this floor space here, this entire square around. So if each can has a diameter of 12.5 centimeters, then all the way from here to here, it's going to be 125 centimeters, 12.5 times 10. The same from left to right, and so this square that we're going to use up just has an area of 125 times 125, so 15,625. That is in centimeters squared. All right, the display in question 7 is changed to have a triangular base. So the top 3 layers are shown, and we want to draw and describe the pattern in the number of cans in each layer. All right, this one's a bit trickier than the other one, but let's do it. All right, so let's get layer 1, 2, and 3 are given. Layer 4 looks like it'll just look like this, 5, 6, and so on. So let's look for a pattern here. I'll just write all the number of circles or the number of cans in each layer. So I do notice that this is not a linear pattern because this goes plus 2, but this one doesn't go plus 2, plus 2, plus 2. Let's see if it's quadratic. This one goes plus 2, then plus 3, then plus 4, then plus 5, then plus 6. If you guys remember from quadratics, that's called the first differences. So if you take each term and you subtract the term before, you see that it goes up by 2, then 3, then 4, then 5, then 6. These are called the first differences. That means if these are not the same, so 2, 3, 4, 5, 6 are all different, that means that our pattern is not linear. But let's look at the second differences. If you actually subtract 2 from 3 and 3 from 4, we have, this is just plus 1, plus 1, plus 1, plus 1. These are all the same. So that suggests that we have a quadratic pattern. All right, so we haven't gone through quadratics yet this year, so without boring you with the details right now, we're going to easily find out that, our leading coefficient is going to be 1/2. This is going to be a quadratic, and right now I could just find that each layer is going to have, the number of cans in each layer is going to be the layer number squared plus, for example, since I know it is quadratic, I know I'm going to have to square 5 for the 5th layer, so that's going to be 25. And I could add another 5 for 30, and divide that by 2 to get 15. For 6, you do the same thing. You do 6 squared, 36, plus another 6, which is 42, and divide by 2, you got 21. See, 4 squared is 16, plus 4 is 20, divide by 2, you get 10. So any layer, you're just going to do n squared plus another n, divide by 2. All right, that was a tricky one, but part B will be a little bit easier for now. How many cans are in the bottom layer? The bottom layer is when n is 10, and so we just know that t of 10 is equal to 10 squared plus 10, so 110 divided by 2, 55. So there will be 55 cans in the bottom layer. All right, part C is a tricky one. Determine the amount of floor space needed for the display. What assumptions are you making? Different people will have different interpretations of this question. For me, I still think that the space in between these circles is useless space, so I'm not going to count it. And even the spaces in this area is kind of useless, so I'm not going to count it. I'll just make a triangle around here. But right here, this tip here, I think that is useful space. I think you can, use the space on the floor that's sort of like on these corners here, right? You can go a straight line around here, but then you can kind of round the corners of these triangles. So I'm going to actually do that. I'm going to see how much space is used up with these with a rounded corner triangle. Let's see what happens here. Now I could think of a few different strategies here. I can think of maybe making a triangle around this thing and then just finding out the area of these little corners inside here and subtracting it. Also, I'm going to try a different strategy. I'm going to put a triangle from the center of this circle in the top all the way to the center of this bottom left to the center of this bottom right and make a triangle there. Calculate the area of that triangle. That should be easy. And then we'll add on the extra, like you're going to have a box here, a box here, and a box here. Those are going to be 3 rectangles. And then we could just add on the little bit of extra space we have in the circles. So it's going to be a little bit of work, but let's get to it. All right, starting with this inside triangle here, we're going to look at the base is going to be how many cans? It's going to be 1, 2, 3, 4, 5, 6, 7, 8 cans, plus a half a can here and a half a can here. So 9 total cans. Each can is 12.5 centimeters long, or in diameter. So 9 times 12.5, that's 112.5 for the bottom. Now to calculate the area of this, we're going to also need the height right here. That'll be a little bit of a challenge because it doesn't tell us. The cans aren't like straight up and down here. But we do know this length, and we do know this length, and we do know this angle is 60 degrees because this is an equilateral triangle. So 60, 60, and 60 are the 3 angles. We know this angle right here is 90 degrees. So we could simply say that, let's say this right here, this side down here, is half of the bottom. So 56.25. And we can say the tangent of 60 degrees is equal to the altitude over, so the height there, over 56.25. You guys know I like to put a 1 here because it helps my students keep things on top, the bottom on the bottom. We're going to knock this 56.25 out of here, bring it over to here. And so A is just equal to the tan of 60 degrees times 56.25. That's approximately 97.4. And we're just going to use that number. I'm not going to erase it from my calculator and multiply because that's the height. We're going to multiply by the base and divide by 2. And I get an area of 5,480.3 approximately. All right, next let's grab one of these rectangles. All 3 of these rectangles are the same anyway. And let's calculate the area of those 3. So this length here is the same as the base of the triangle, 112.5. We can see the height will just be the radius of one of these circles. So 12.5 divided by 2, because the diameter is 12.5, so 6.25, and simply the rectangle is base times height, or length times width, however you want to say it. 6.25 times 112.5 equals 703.125. Now keep in mind there are going to be 3 of those, so we can just multiply by 3 and say 2109.375. Right, so we've got our inside triangle, we've got our 3 rectangles. Now all we have to do is these little pie shapes on the side. All right, let's take one of these circles and take a look at it. If I wanted to find the area, that's simply going to be pi r squared. Right, so pi times 6.25 squared. All right, for now we're going to see that's 122.72 approximately. But that's the area of this full circle. As you can see, there's this whole area where we don't want to calculate, and then this one little area is what we're trying to calculate. Right, so let's just look at the angle over here. We know this is a 90-degree angle. We know this is a 60-degree angle, and we know this is a 90-degree angle. So 90, 180, 240 degrees of this out of the 360 degrees we don't want. Right, so we're left with 120 degrees of that 360 degrees. That's 1/3 of this circle. So the area is actually 1/3 of our 122.72. I'm just going to keep the whole number in my calculator and divide by 3. So the area of this one little section is 40.91 approximately. However, we want 3 of those. So let's multiply that by 3, and we're right back to 122.72. That's the area of all 3 of those put together. So all 3 of those make up one full circle. Alright, so we're almost at our answer here. We have the area of our triangle, all of this. So the cans take up all that space for sure. And then we have the area of 3 rectangles. You got one here, one here, and one here. And then that doesn't quite take up all the room that we want here. We still have this little shape here, little shape here, little shape here. All of those are 1/3 of a circle, right? We knew that these were 60 degrees because each one of these angles is 60 degrees because the triangle is an equilateral triangle. And the 3 of those together gives us the full area, which is 5480.3 plus 2109.375 plus 122.72, 7,712.395, and that is in inches squared. And of course, that's under the assumption that all the space between these circles doesn't count, like that counts as space that we're taking up from the floor. But not on these little corners here, because that's not between circles, that's on the outside. Alright, for part D, will the display hold more or fewer cans than the display in question 7? Justify your answer. Alright, well, I know the 10th layer in itself for question number 7 had 100 cans, 10 by 10. This one only has 55 cans, so already quite a bit less than in question 7. But each layer, each layer is the same number on this base as the layer before. So it's the second last layer, and the other one had 9 cans across and 9 cans up. This one has 9, 8, 7, 6, 5, 4. So obviously the question number 7 has way more cans because each layer, like on this one when there was only 8 cans across, this one has 8, 7, 6, 5, 4, whereas the other one had 8, 8, 8, 8, 8. So each layer there are more cans in question 7. So obviously there are far more cans for question 7 than in this display. Question number 9. A decorator is painting this wall of an attic room. The window measures 0.6 meters by 0.5 meters. Here's the room. What is the area of the wall in square meters and square feet? And we have over here our conversion. Now, be very, very careful. 1 meter is equal to 3.2808 feet. But that does not mean that 1 meter squared is equal to 3.2808 feet squared. And this, we're talking about area. So we want meters squared and square feet. Okay, so let me just show you a little diagram that might help. So 1 meter, let's just say that this is 1 meter long and 1 meter wide as well. All right, this line right here is 1 meter. but this square is 1 meter squared. So if you're just measuring a distance, you're going to measure how many of these lines could go along that distance. If you're measuring area, you're saying how many of these squares can I fit onto that wall, right? Well, 1 meter is equal to 3.2808 feet. So I'm going to get 3.28 feet in here. But if you notice that 1 meter this way is also 3.2808 feet, and so this 1 meter squared is not 3.2808 feet. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, and then all of these add up to a little bit more. We actually have 0.28 of a square right here, another 0.2808, another 0.2808, 0.8. So we have a bunch. So that's like more than a quarter each. 1, 2, 3. That'll make up an extra one and a bit. So in the end, we actually have a square of over 10 feet squared. Right? So yes, 1 meter is equal to 3.2808 feet. But 1 meter squared, which is this blue part, is not just 3.2808 feet squared. Look at, there's 1 foot squared, 2 feet squared, 3 feet squared. 3.28 just covers this top. You have another 3.28 and another 3.28 and then, well, 2808. And you actually have another 0.2808 of 3.2808. Right? So it makes up more than 10 squares. So 1 meter squared is actually equal to 3.2808 times 3.2808 feet squared. So using my calculator, I can see that there are 10.7636 feet squared approximately in 1 meter squared. So this is actually a common problem in high school when it comes to converting from meters to feet or converting between any two units, is that when we're doing it in squares, then you actually have to square the number that the conversion is as well, right? Because you have to keep in mind that just because there's 3.2808 of them this way doesn't mean that 3.28 of the squares will cover the whole square, right? So you'll always have to do 3.28 times 3.28. If it's going to be even worse when we work with cubes, right? With cubes, you're going to have to do it 3 times, 3.2808 times 3.2808, and then you're going to go in the third dimension, 3.2808. And so actually 1 meter cubed is going to be equal to 3.2808. You're going to have to cube it. So 35.3134 approximately feet cubed. That means if I have a bunch of little 1 foot cubes, 1 foot, 1 foot by 1 foot by 1 foot cube, we can get 35 of those guys inside a 1 meter cube. All right, that was the hardest part of the question, just getting that conversion thing out of the way. Now let's do the easy part. All right, looking at this wall here, I can see that the shape is a trapezoid. These are 2 parallel lines up and down, and minus a rectangle for the window. So basically we want the area of the trapezoid minus the area of the window. And we're going to want it in square meters and square feet. So let's first find it in square meters because we have meters listed here. All right, the area of a trapezoid is the average of this rectangle, the smaller rectangle, 1.5 times 4.3 meters, and 2.2 times 4.3 meters, the larger rectangle. Right, so the average of those two is going to be the area of this trapezoid. So we got area equals, first we want to find the average of 1.5 and 2.2, so 1.5 plus 2.2 divided by 2, and we'll multiply that by this length, 4.3 meters, and we get 7.955 for the area of that trapezoid. Now we have to subtract the area of that little window, which is 0.6 by 0.5. Well, 6 times 5 is 30, so 0.6 times 0.5 is 0.3. Therefore, the area of that wall, not including that window, is 7.655 meters squared. Now we just need to convert to feet squared, so we're going to multiply by 10.7636, and that'll be 82.395358. So let's say 82.4 feet squared. And for part B, the paint is sold in 1-pint containers. Each container should cover between 50 square feet and 60 square feet. How many cans of paint should the decorator buy? Well, we have more than 50 square feet, but we have less than 100 square feet. So it looks like we need to buy 2 cans. All right, number 10. The running track in this diagram consists of 2 parallel sections with semicircular sections at each end. Determine the area of the track. So this is the gray area that we're trying to find the area of, not the green area. All right, let's take a closer look here. Now my strategy here is going to be to break this up into rectangles and circles. All right, let's start off. Basically, we have 2 rectangles here in gray, and we have one sort of a ring here in gray that's going to be equal to the area of this gray. All right, so one strategy would be to find the area of this whole rectangle and then subtract the green part. But I'm not even going to do that. I think it'll be easier just to find the area of each one of these gray rectangles individually. And maybe it'll be about the same. Right, so I know that the length here is 85 meters, as we see up here, and from this width of the track, well, I know from halfway point down to the bottom is 46.41, and from the halfway point just to the edge of the track is 36.41. So that means the track has a width of 10 meters, 46.1 minus 36.1, and that's going to be the same for both sides. Right, so the area of each one of these rectangles is just 85 by 10, 85 times 10, so 850 meters squared. Now for this circle, I'm going to take a different approach. I'm going to find the area of the whole circle, and then I'm just going to subtract the area of the green part. Well, the whole circle has a radius of 46.41, as we can see up here, and the inside circle has a radius of 36.41. So we simply do pi r squared for the area of the big circle, so pi times 46.41 squared, and pi r squared for the inner one, so pi times 36.41 squared, and we simply subtract the area of the smaller one from the area of the larger one, and we have our total area. Alright, last but not least, we want the area of the entire track, so that means one of these rectangles, which is 850, another rectangle, which is another 850, and the ring around here, which is 2601.87. So we just say the total area equals 2601.87 plus 850 plus 850. So the area of the track is approximately 4,301.87, and that is in meters squared.